Hello students, this is a course on analytical mechanics or analytical dynamics, and this is targeted towards students in their final bachelor years like BSc and also first year MSc. Okay, this will also be useful for students who are doing their BTech in different Indian universities. The goal of this course is twofold. One, we want to develop the language that will enable us to comprehend the world around us in its details, and what we are really interested in is the details at the fundamental level. Okay? And the second, we would like to learn to appreciate and cultivate the thought process that leads to the formulation of questions in their ever-increasing, cleaner and deeper forms, which will lead us to a deeper and much more beautiful forms of understanding of the world around us. So that's the goal at a deeper level. And of course, as we go around, we'll be learning things in this subject. So let me start by recollecting what we already know, what you all have seen in your physics courses. So I start by writing this very familiar equation. Okay, that's the Newton's second law, which says that the acceleration, which is a vector quantity, okay. So let's say we are imagining a particle which has mass m, okay, and it is subjected a force F, okay. Then it will accelerate according to this relation. Okay, that's your Newton's second law. Let me write it in a slightly different form, which will be useful to ask further questions. So instead of writing A for acceleration, let me introduce the following notation. I write vector r at any time t to be the Cartesian coordinate of the particle with mass m. Okay, so r would be the Cartesian okay, and instead of writing A, I will write r double dot, and these two dots signify that I am taking a second derivative with respect to time. Okay, that's what r double dot means. So with this I can write r double dot as force over mass. Okay. Let me also specify the arguments that enter into the force. The force could, in principle, depend on where the particle is at the time t. So it could depend on the r, okay. It could depend on velocities, how fast that particle is moving. It could depend on other things, and it could also depend on time. Okay. Now, when you look at this equation, what comes to your mind? And there are several things which we can think of. One is at a very philosophical level. You see, what this equation is saying is that if you tell what are the forces this particle is experiencing, okay, if you tell that, I can tell what the acceleration is. Now, if you know the acceleration at any point of time, then you can integrate that equation and get the trajectory. You can tell where the particle would be at any later time t if you solve this equation, and also on the top of it you have to specify initial conditions, where it was at time t equal to 0, how fast it was moving at time t equal to 0. Okay? That information will be sufficient to tell all this. So coming to the philosophical thing, it's non-trivial that there are such laws. Okay, it's a non-trivial statement that we can predict what will happen later. Okay, that's the philosophical thing. But let's say we agree upon that universe is describable by laws. Okay, that what can more be asked from this equation? Okay, you can ask why it is second order. Okay, why only derivatives which are second order, d2t over dt square involved in this relation. Now that has to come from your experimentation experiences. You see, when you say it is second ordered in a time derivative, it means that the solution will involve two constants of integration. You see, when you integrate it first, you will get down from r double dot to r dot, okay, and you will have a constant of integration, let's call it C1, which cannot be determined by this equation, that's a physics input. Then you integrate once more, you arrive at r, that is what you are looking for, but then at this stage you get one more constant integration, C2. Okay, so two constants of integration you will have, which you typically know that they are the coordinates at any time t, at any initial time, let's say t equal to 0, and the velocity of the particle at the same time. You could use them to fix what C1 and C2 are. Okay, but I mean, why should this be a second order differential equation? Okay, could Newton have chosen this to be a third order differential equation? Could he have written something involving three derivatives? Okay, that's one thing you can ask, and it's not a very difficult thing to answer. Okay, imagine we could, then it would imply that I have a relation like this. Okay, I'm keeping up to the second time derivative in here. So all derivatives lower than r triple dot, I keep on the right hand side in the definition of force. Okay. Okay, let's see what happens if you try to write down such an equation. Okay, let's say we take a particle which is free, there is no force acting on it, so I can put down the F to be 0. Okay, let's say I take a particle which is free. Okay, by free I mean no forces acting on this one. Then you have r triple dot 0. Okay, now if you write down the solution of this equation, okay, this will involve three constants of integration, vector A, vector B, and vector C. Okay, remember this equation, for example, here it's not one equation, it's three equations. There is one equation for each Cartesian component. So one equation for Rx, okay, one equation for R, instead of Rx I can say X, Y, and Z. Okay, so these are the three. So you should read it as X triple dot as 1 over Fx, Y triple dot as 1 over M Fy. Okay, so these are really three equations. So each vector equation becomes three equations. Okay, so coming back to this, if you solve it, you'll get such a result after integrating. And clearly, if you choose time, the particle to be at rest at time t equal to 0, so you put r of 0, that would be your C. Okay, so this you can fix by telling where the particle is located at time t0. Very good. Similarly, the B you will be able to fix by telling how fast it was moving or what the velocity was at time t equal to 0. Okay, you take one derivative, this C will be gone, this will leave only B behind, and this will involve t, put t equal to 0, this term is also gone, so you have only B left. So you will be able to fix B by initial velocity. Okay, and as you can see here, that this A you will need to specify, for example, what the acceleration was at time t equal to 0 before you could really tell what r at any time t would be. Okay, so this constant will not be determined by telling just the coordinate and the velocity at time t equal to 0. You will also need to specify the acceleration at time t equal to 0. But you already know from your experience that that's not how our nature works. You just need to tell these two things, where and the velocity. You don't need to specify acceleration to know where it would be at any later time t, which means that your equations should be second order differential equations, and these are ordinary differential equations, and they cannot involve terms which are derivatives in time more than 2, okay, cannot have second order, third order or fourth order. That's one thing about the equation, which was our force law. Now let's move to something even deeper. Let's say we have established that indeed, if I solve this, this Newton's equation, I will be able to tell the future trajectory. Okay, imagine you have n number of particles, lots of particles in your system, and each of them is, let me put an index I to emphasize particle number I, not necessarily I here, the force could depend on the coordinates of all the particles. Okay, so let's say I runs from 1 to n. You have n number of particles in your system, and j also runs from 1 to n. Sorry, this is 1. Okay, so what this equation is saying is that the acceleration of ith particle at time t would be determined by what force it is experiencing, and that force depends on the coordinates of other particles and their velocities and time t. That's the most generic thing which you can write. Now let's ask, can we say something more without going into the details of the system based on our some general understanding of how the world is? Okay. One thing you clearly know from your education for previous years, that if I do an experiment now, okay, whatever results I get, I will get the same results if I were to do that experiment, let's say 100 years from now or 1000 years from now. Okay, meaning it does not matter when you do that experiment. This is this can be put more formally as saying that the time is homogeneous. Okay, so what I'm saying is there exist frames of references in which time is homogeneous, which means whether you do experiment now or 1 billion years from now, the results will be identical if you have arranged everything identically in these two different times. Okay, that's one thing. So there are frames, special frames called inertial frames, in which time flows in a homogeneous manner. Time is homogeneous, okay? That's nice. There is also another fact which you definitely know, is that if you take your experimental setup, okay, whatever experiment is happening, you take this thing, and instead of doing it here, let's say you do it a million kilometers away from here, okay, or billion kilometers away. Whatever results you will get here is the same you will get by doing the same experiment millions or billions of kilometers away. Okay, so this location is in no manner special compared to any other locations. All locations are equivalent, meaning if I take my setup and translate it to another location, this way, that way, okay, this way, whichever way you take it, if you do a translation by some amount A is a vector, okay. If you translate everything by amount A, your results will not depend on the choice of A, okay. You do the experiment wherever you wish to, and this is more formally said as the following. So you say that space is homogeneous, okay. All locations are equivalent. That's what this sophisticated sounding sentence means, okay. And that's the property of a special kind of a frame which we call inertial frames. There's still more one thing which you know, is that if you take your experimental setup, okay, and now I'm not putting it somewhere, I'm not taking it in a different place. All I want to do is take this experimental setup and reorient it. So instead of, let's say, something was going from here to there, something was being measured here, there were forces, that you take the entire setup and rotate in this way, okay, or this way, or whichever way you like. Doing this rotation will also not change the outcomes of your experiment, okay. All orientations are equivalent, and this we say more formally as that space is isotropic, okay. Isotropic meaning equivalent in all directions. So I say space is isotropic, SPAC, space is isotropic. Okay, very nice. So you see what we have written down is really nice. We are not telling about what will happen to a particle when it is in such a frame. We are telling things about how time behaves in such frames. See, generally when you talk about inertial frames, you'll be told that if there is a particle and it is not acted upon by any forces, if it is at rest or if it is in uniform motion, it will remain so, okay, that's how you say. But now we are describing inertial frames not by appealing to what happens to a particle, but rather saying what is the nature of time in such a frame and nature of space in such a frame, okay. And this will be very useful for us in understanding our laws of nature, okay. So we have, let's put it in a box, and we'll try to make slightly more mathematical statements based on it. Okay. Okay, now you say that's all nice. You have something about some understanding of inertial frames. Now, what can we what more can we say now? Well, one thing it's clear that the system of your particles, which is, let's say we are looking at an inertial frame, okay, then that system of particles should somehow know that they are in an inertial frame. They have to know that time is homogeneous in this frame, that space is homogeneous, that it is isotropic. What part of the system knows about these things? And clearly, let's write down our equation of motion. So we had, let's go back here, I think here, this thing, okay. Now if I'm saying that each particle is going to accelerate according to the forces, then it has to be those forces which will know about the frame, right? There's nothing else on the left hand side. Left hand side is just the acceleration of that particle. And how much to accelerate and in what manner is told to it by the forces, which is on the right hand side. Okay, so the right hand side has to know about this information which we wrote here. Okay, so let's have a look at this. Should I write? Okay, let's write it again. So I want to now talk about first homogeneity of time. These are okay. So MI RI double dot is force on ith particle, which depends on where each particle is located at that time. Okay, I'm suppressing the t here. I could have put a t here as well, which I'm suppressing for now. J and t. Okay, that's what we wrote earlier. Now let's see what homogeneity of time has to say about the forces. Now imagine you are doing the experiment now, okay, and all the forces are behaving whichever way they behave, and you get the accelerations of each of the particles at this time. Okay. Now as I said, you can do the experiment 1000 years later and you should expect everything the same, meaning all the particles will move around in time in exactly the same manner. But that can happen only if the forces do not change over time, right? If I start doing experiment 1 million years later, and because of this time dependence, forces change and everything will change. Okay, the evolution of the system will not be the same if the forces depended on time. So clearly, this T cannot appear in the force. Okay. Now remember, I am talking about a system which is insulated from or isolated from all other things. The system is self-contained. There are no external forces on the system. Whatever forces individual particles are experiencing, they are due to all other particles in the system. Okay, that's very important. Otherwise, what I'm saying is not true. So that's nice. We have said that the forces in an isolated system cannot be function of time. That's already a progress. Let's see what homogeneity of space implies. Okay, again let me write it down. Force on the ith particle. Okay. Now you see, here we are saying that we need to know where exactly each particle is located. So let's say a system of 2 or 20 particles, it doesn't matter. Look at 2 of them. Okay. Let's look at the force on a particle here. I'm saying the force on this is determined by the particle here, there, there. Okay. It really depends on Rj, where j runs from 2 to n. Let's say this is particle number 1. Now because of homogeneity of space, if I take the entire setup and move to some other location, if I do a translation by a vector a, so let's say just translate everything along x-axis, nothing should change, right? Whether an experiment I do here or take the entire box, put somewhere else, nothing should change. which would mean that the forces should not care about where this guy is, where that guy is, what are the exact locations of those other particles at time t. But what it should care about is what is the separation between this and that. We are talking about the forces on this. So separation between this and that, separation between this and that, okay, this and that, this and that. Because everything should give the same answer if I translate from here to there. Meaning the forces cannot depend on the locations of all the particles, but rather only on their differences. Okay? So I will write Rj minus Rk. Okay, and K and J and K run over all the particles. Okay. T anyway was already gone. So you see, we have been able to put much more restriction on the nature of on the arguments that can enter into the force. Instead of having this full freedom here, now we have much more restricted form. T is gone and the coordinates cannot appear directly, they can only appear in differences. Okay, that's good. How about the homogeneity? Okay, homogeneity we have taken care of. Let's talk about the isotropy. Or even before I do isotropy, let me okay, isotropy. Let's talk about, we'll come to isotropy later. Let's talk about something else. There's something more we know about nature, is that if you are doing an experiment in one inertial frame, whatever that frame is, okay, I will not go into details of how you find an inertial frame, that I believe you already know. If you are given an inertial frame, okay, and you take another frame which is moving in with the constant velocity with respect to this frame, okay, then both the frames are inertial. Whatever physics you see in the first frame is exactly what you are going to see in the second frame. Okay, physics will not change by moving from this inertial frame to another frame which is in a uniform motion with respect to the first one. Okay. Now I want to put this information into our equations of motion, meaning it will be clearly the force which will know about this. So this, let's call it relative motion. Of frames. Okay, FRAMES. Okay, so what will happen is this will be, now already you had Rj minus Rk from the homogeneity of space, time was already gone. Now if you go to another frame in which is moving with some velocity v with respect to the first one, all the particles, whatever their velocities were at time t in the frame number 1, will change to the velocities what they had plus the velocity of this frame, right? So all of them will get, all the velocities at time t will get added by this fixed amount, okay, which is the relative velocity between the two frames. So clearly, because the physics is not going to change, the force should not care about what the velocities are in a given frame. Okay, what are the velocities of each of the particles in that given frame? What it should care about is only the relative velocities. Because when you go from one frame to another frame which are moving with respect to each other, the relative velocities are not going to change. Okay, because when you take the difference, the additive part drops out. Okay, so which means that I should not have Rj dot, but I should have Rj dot minus Rk dot. time was anyway gone. So these are the constraints which we have been able to put on the forces. And let me give you one example which is very familiar to you, so that you can see that indeed the forces which you already know are of this form. So let's go back to our Mr. Newton, okay? Newton's force of gravitation. What is it? So let's say you have two particles, particle number 1, particle number 2, okay? Some origin O, and I say this is the coordinate R1, that guy is at R2, these are the vectors. Now I want to know the force on the first one. Clearly the force on the first one will be directed towards 2 because it is being pulled into 2. It's the gravitational force. So the force on particle number 1 would be G m m over r square. It's a inverse square law, you know. And then you have a unit vector where this is the unit vector, okay. I can write down r hat more clearly for you. It will be r2 minus r1, okay. You see this is r2, r1 if you subtract, this is what you'll get, over r2 minus r1 modulus. That's the magnitude of it. So that's why this is a unit vector, and this r is just r2 minus r1 modulus square. Okay, you see the force depends only on the differences in the positions of these two particles. It doesn't care where this guy is and where that guy is individually, but only on the differences. Here you also don't see any time, and in this force there is no velocity involved. Okay, that's all for this video, and we'll start talking about, I believe, more about the coordinates which we should use in studying different kinds of systems. What kind of coordinates are suitable? We'll have a long discussion on that next time. Okay, see you.